Hi all. So as we all know, Kafka is being used as a high-speed distributed streaming platform. Today we are going to discuss why Kafka is so fast and how it can handle millions of messages per second. So let's consider this as a Kafka cluster. So there are multiple brokers in it. So broker, you can think of any Linux server or machine. So in the Linux machine, you have RAM, disk, processor, etc. Right? And within the RAM also there are multiple segments. There is a segment for Linux kernel space, and there is JVM heap memory, etc. Right? So when it is trying to insert any message into the hard disk, the operating system first it will store it into a cache segment called OS page cache. Once that is inserted into this, from here it will flush it into the disk. So this is how it works. Now consider a typical flow where the producer sends a message to the Kafka cluster. So once the request received by the broker, the first point of contact at the broker is the TCP socket. So the TCP socket sitting at the network layer will receive the message or receive the request, and it will be stored in the socket buffer memory inside RAM. So this is the step 1, and then it will be moved to the heap memory, and then finally while moving into the disk it will be first moved to the OS page cache, and then it will be flushed to the disk. So these are all the steps which are involved while a message has been written by a producer into the Kafka. So I will write it down. First the producer will send a request, and the request will be received and written into the socket buffer, TCP socket buffer, which is inside RAM, and then this will be written into the heap memory, JVM heap memory, again inside RAM, and then it will be moved to OS page cache, and then it will be written to the disk. So it will these three things, socket buffer, heap, and OS page cache, all belongs to the RAM. And the hard disk, there are two kinds of disk. One is HDD and SSD. HDD, you all know, hard disk drive. So this is a magnetic storage. It is very slow, and it's a old technology. And SSD means solid state drive. It uses latest technology like flash memory chips, which is very fast. So nowadays most of the companies are using SSDs for high speed systems, high speed disk accesses. So let's consider a request and see the time taken at each stage, so that we'll understand for one message how much time it takes and how Kafka optimizes that to in order to make sure that it is able to process millions of messages per second. So for example, the first thing what we need to consider is the request flow. So from the producer, the request will go to the Kafka, right, over the network. So the first thing we need to consider is the network. So how much time it takes for a request to go from producer to Kafka and the response to come from Kafka to producer. This is called network round trip time. So I will take some approximate numbers to understand how it works. So let's say it takes approximately zero point zero 0.05 milliseconds for a request to reach the Kafka server, and then from Kafka server the response reaches to the producer. Then the second step is, once the request is received at Kafka, what it does, it initially has to parse it, right? It has to parse it, understand it, then maybe you need to authorize it. So there are multiple more steps that will be done for every request before actually storing it into the memory, correct? So these steps also will take some time. Let's consider this is also zero point 0.5 milliseconds. And the third step is actually writing into the memory. So store the request initially into the socket buffer, right? In the RAM in socket buffer it will be stored. Then it will be stored in the JVM heap memory, and finally it will be stored in OS page cache. So after this, it will be stored in the disk. So these all three are nothing but again RAM only. So RAM is very fast. So it will take less than 1 microsecond to write a message into the RAM. Again, disk is slow. I'll consider only SDD for now. So even SDD will take 1 millisecond, for example. So now these are the numbers. Okay, let me, for every request, these two will happen, right? So let me club it together. This is zero point 0.1 millisecond. So in total, we have for one message, for a producer to send it to Kafka and write it into Kafka and then get a response, it takes zero point 0.1 milliseconds for the network round trip and the parsing, then 1 microsecond for writing into the different parts of RAM, and 1 millisecond for writing into the disk. So if you take it approximately, 1 millisecond means 1000 microseconds, which means RAM is 1000 times faster than the hard disk, the disk. And if you think about the network round trip time, even zero point 0.1 millisecond means 100 microseconds. So even here also it is 100 times faster than the network round trip time. So RAM is so fast. So if you take the approximate time, so we can think 1 millisecond is the approximate, because microsecond is negligible in front of millisecond. So for one message it takes 1 millisecond. For 1 second, how many message can be processed? 1 second is nothing but 1000 milliseconds. So 1 millisecond one message means 1000 millisecond 1000 messages. So 1000 messages it can process per second. So do you think this speed is good enough for a system like Kafka? Not at all, right? So if you take real-time applications like Amazon, Flipkart, Zomato, Facebook, they process millions of messages per second. So 1000 is very, very, very low. So what to do now? We have to reduce this. So out of these three times, these three places where it is taking this time, who is the culprit? So definitely this one, right? So this is taking huge time when compared to other. So this is nothing but the time it takes to store it in the disk. So how to solve this issue? So one idea is, let's remove disk from the request response flow. So that means the producer will send a request and the message will be written into socket buffer heap OS page cache, but we won't write into the disk immediately. We will right away respond to producer saying, hey producer, your message has been written successfully, but we will move the message to the disk asynchronously. So that means without sending it to disk itself, we are informing producer that your message is successfully written, but slowly asynchronously we are doing that. There is it, we call it as fsync. So instead of doing the fsync to push the data from cache to disk, we are doing the fsync asynchronously. So this is the technique that we are going to use to increase the speed. But what is the problem here? For example, let's say there is a restart happened inside the broker one. So that means I'll take some example. For example, at 10 o'clock, 00 minutes, 00 seconds, 0001 second, 001 millisecond, producer send the message. At the same time, and 002 millisecond, it was written in OS page cache by the Kafka and then responded to producer saying, hey, it has been written. So, but during 0.003, we are about to write it into disk, but a system restart has happened suddenly, or due to power failure, the system has shut down and we have to start it again. So that means by the time it starts, all the data inside the RAM is removed, right? Because RAM is volatile memory. So as soon as you restart it, everything inside the RAM will be gone, and you haven't stored that in the disk yet. So that means your message is gone. So will the producer be happy? Producer thinks that his message is safely written inside the Kafka. So he was in that assumption, but later when he comes, he gets to know that it was not there in our Kafka, so which is wrong, right? So how to solve this issue? So for this, Kafka is using a concept called replication. So let's say in Kafka, Generally, we maintained data in messages in partitions. So for every topic, topic 1, partition 1, we maintain data in this way, and the same partition will maintain multiple replicas. So the same topic and same partitions will be there in broker 1, maybe in broker 3 and broker 5 will have the same data, but only one is the main one. So in this case, for example, producer always writes messages only to the main broker. So this main broker is called leader. For every partition, there will be one leader and the others will be followers. So this is follower 1 and follower 2, which means when the message comes here, all the followers will continuously poll the leader and see if there is any new message arrived. If so, they will copy in their systems as well. So now what we do in the broker 1, we are storing the message in OS page cache, right? Even in broker 3 also, they will copy it into page cache only, and then once it is copied in the page cache which is in RAM in their brokers, once it is written in the page cache, then they will respond to producer saying, hey, the return has been successful. Even now also they don't push it into disk. Without pushing into disk, just in the OS page cache, if the message is present, they will send the response to producer saying the message has been written successfully. Now what is the risk? Let's say the broker 1 is down again, it has restarted. No problem, because we have the same message in the RAM, specifically in the OS page cache of B3 and B5. So one will become later out of these two that will have the data. If the broker is up again, B1 is up again, it will become follower for this leader and it will take the latest messages and get it updated. So there is no problem, right? So you may say that okay, there may be power failure in all the systems, three servers at the same time. So to avoid these kind of cases, what they do is they do all the precautions, like they maintain power backups like UPS, so that they make sure due to power issues the system should not be down. You may say that maybe due to some calamity, all the three servers are present in same data center and there was some floods happening in the city. All the data center got uh, has gone. So now all the servers are not accessible. So what should we do? So for this reason, generally the replication is maintained in different geolocations. So it's not present in the same city. One replica is present in one city, maybe the other replica is present in other city. That is how they do the replication to handle the fault in these kind of issues. And maybe one more thing they can do is if there is any software patches or restarts happening, so those things they will do it by rolling basis. They don't update all the systems at once. They do the deployments or patches in the rolling windows. So these servers restarts at some certain time, these start at certain time, so that way we don't fall into the risk of all the systems are failed at the same time. So this is how Kafka is handling. Uh, Kafka is making sure that the data is not missing. So data is durable or persistent. At the same time, it is very fast, right? Even then, you may say that if there is a 0.0001 percentage chance that all servers may restart or fail, but the data is missing, right? So in that case, let's say you are working for a military application. In military, that for that application every message is important. You should never lose even one message at any point of time. In that case, you don't have any choice but to, for every message you have to push that message into the disk, then only respond to producer saying, hey, your message has been written. So this fsync has to be done for every message. But what is the problem with that? You are impacting the latency. So it is adding 1 millisecond to it. So you could process only 1,000 messages per second, which is very slow. But if you insist like that, because you want, you should need 100% consistent systems or 100% correct systems. Data should never be lost. Then you don't have any option. Maybe if you want 10,000 messages per second to be processed, you have to take 10 more brokers. So you have to increase the infrastructure to improve the efficiency of it. Other than that, I mean, normally we cannot achieve that otherwise. So that is how you can do that. So this is the first part of it. So now the 1 millisecond has been removed from this picture. So right, we are left with only two things here, 0.1 millisecond and 1 microsecond. Let me write it down. So for one message, now it takes 0.1 milliseconds for network round trip time and parsing stuff, and 1 microsecond for writing into RAM. Now, approximately it is also equal to 0.1 millisecond, right? So in if one message can take 0.1 millisecond, in 1 second, how many we can process? 1000 milliseconds, right? 1 millisecond means 10 messages into 10, which is 10,000 messages per second. So do you think this is good enough? Still no, right? You want to process millions of messages per second. 10,000 is even low now. So what should we do? We have to remove this also from the picture. Can we do that? Without network, can we send a request and response? Not at all, right? So what is the solution here? So for example, for one message, if it is 1 KB size, if you are sending that in one request, it is taking zero point 0.1 milliseconds for the round trip time and parsing. Now what I'll do is I'll club 100 messages, so which will become 100 KB, but I'll send them in a same request. Request is same. Messages are clubbed, but in the same request. Do you think the time will increase? No, right? Because this millisecond is for one request to go to over the network to the server and get back and then parse. Even here is the same thing. You are still sending one request. One request is only going over the network and they're parsing only one request and sending the response. Still approximately it will be 1 millisecond, 0.1 milliseconds only, right? So now this is called batching, which means the producer have to send the messages in batch, like 100 messages in one batch, like that. So he will send all messages together. Even the consumers also, they will read the messages in batches to improve the efficiency of it. So now let's see the time it takes for 100 messages. The whole time it takes 100 messages for network round trip and parsing is zero point 0.1 milliseconds, as we know. Now for storing it into RAM. So as we know, it will take 1 microsecond to store it into RAM. Now for one message it takes 1 microsecond. For 100 messages it takes 100 microseconds, right? Which is nothing but 100 microseconds, which is nothing but zero point 0.1 milliseconds. Here I am considering replication also. On an average I am taking 1 microsecond. This is to write the message in multiple machines in the RAM into the OS page cache only. So this is zero point 0.1 millisecond plus zero point 0.1. Approximately I'll take zero point 0.1 only instead of zero point 0.2 to make the calculation easier. So zero point 0.1 millisecond. So 100 messages are taking 0.1 millisecond. That means in 1 second how many messages can be processed? 1000 milliseconds. 1 second equal to 1000 millisecond. In 1 millisecond you can process 100 into 10,000. So which is nothing but, which is 1 million. 1 million messages per second. So we have achieved it. So by sending the messages as batches, we were able to process 1 million messages per second. This is good enough, right? So what we have done so far, one is we have avoid writing into the disk, but we use replication there to make sure that the data is not lost. So we are ensuring durability using replication. So no disk. Second one is sending the data via batching. So producer has to send or consumer has to consume messages as batches only. So use batching so that we will send the messages in bulk, so that we will avoid network time, round trip time, as well as parsing time for multiple messages. So along with that, they have done some more small optimization. For example, for when let's say here, even though the 100 messages are clubbed, within 1 second you are still sending 10,000 messages, right? So in 1 second, in 1 second you are processing 10,000 requests. Each request has 100, so it makes 1 million messages, but requests wise it is only 10,000. Messages wise it is 1 million. So for these 10,000 requests, every time you have to make a connection from producer to Kafka. So you have to make 10,000 connections per second. Now let's think in our how many connections you make. Every time it makes a connection, it needs to do a handshake, etc. Right? To avoid that, what they did is they have provided a functionality like you create a connection and make it live for few minutes or few hours. During that time, you can continuously send requests and receive responses. No need to make a connection again and again. So that means they will make a TCP handshake and make sure that the connection is alive, probably for minutes or hours. So this is one more optimization. And one more optimization is, if you see here, I mentioned from socket buffer data is moved to heap and heap to OS page cache and disk, right? So if you see heap now, normally in heap, the data will be stored in multiple objects will be stored. There is something called garbage collector which continuously monitors for objects which doesn't have any reference. If so, it will delete those objects without reference, right? So it's a continuous process. So while doing the deletion, it will pause the JVM. So during that time, no other application or process can use that JVM because JVM is paused by the garbage collector. So it will slow down your application. So to avoid that, what we can do is we don't push the payload into the heap. We just store the metadata here, metadata like headers, etc. here in the heap, and the actual payload will be directly moved from socket buffer to OS page cache, and then to disk. This way, we are avoiding heap to store huge data. We put very light data, little data into heap. This way, we are removing the burden out of garbage collector. So that way we are allowing JVM to run optimally, correct? So that is the fourth one. So we are not using heap memory for payload. Payload is the heaviest part, right? Not the metadata. So this way we are saving the garbage collector to not to pause the JVM. So this is one of the optimization. So by doing all this optimization, Kafka is making sure that it is able to process millions of messages per second. At the same time, it is being durable and optimal and efficient. I hope you understood it clearly. So we'll see you in the next video. Thank you very much.